Have you ever looked up at the night sky and wondered what kinds of worlds lie beyond our solar system? For thousands of years, humans could only dream about planets orbiting distant stars. But in the past 3 decades, astronomers have discovered thousands of exoplanets, planets outside our solar system, each with unique, often mind-blowing features. Some are huge gas giants, some are rocky super-Earths, and some are so strange they seem like they come from science fiction. Today, we are exploring 2 of the most extraordinary exoplanets ever found: diamond planets and glass planets. These are not just fictional concepts. They are real distant worlds, shaped by extreme heat pressure and cosmic chemistry. Get ready to journey 40 to 60 light-years away to see planets that rewrite what we thought we knew about planetary formation. Let us start with the diamond planet. Imagine a world where the ground sparkles like a royal jewel, where mountains are made of pure crystal, and where carbon is compressed into diamond on a global scale. This is not a fairy tale. This is 55 Cancri E, also known as Janssen, the most famous diamond planet in our galaxy. Discovered in 2004 and confirmed as a carbon-rich super-Earth in 2012, this planet orbits a sun-like star called 55 Cancri A, about 40 light-years from Earth in the constellation Cancer. To put that distance in perspective, a beam of light takes 40 years to travel between Earth and this planet, far beyond our current technology to reach, but close enough for our most powerful telescopes to study in detail. What makes 55 Cancri E a diamond planet? Its entire composition is unlike anything in our solar system. Earth is a silicate planet, made mostly of oxygen, silicon, and rock. But 55 Cancri E is a carbon planet formed in a stellar system with an extremely high carbon-to-oxygen ratio. That means there was far more carbon than oxygen available when the planet formed, creating a chemical environment perfect for making diamonds. The planet is about twice the size of Earth and 8 times more massive, classifying it as a super-Earth. It orbits its star at an astonishingly close distance, just 0.015 AU from its star, compared to Earth's 1 AU from the Sunday. 1 full year on 55 Cancri E lasts only 18 hours. Because it is so close to its star, the planet is tidally locked, meaning one side always faces the star, and the other is in permanent darkness. The conditions on this planet are extreme beyond imagination. The day-side temperature soars above 2,700 Kelvin, or more than 2,400 degrees Celsius, hot enough to melt iron and rock. The internal pressure is millions of times higher than Earth's core pressure. On Earth, diamonds form deep underground, about 150 kilometers below the surface, over billions of years under high pressure and heat. On 55 Cancri E, those extreme conditions exist across the entire planet. Carbon atoms, the building blocks of all life on Earth and of diamonds, are squeezed and heated so intensely that they form massive layers of crystalline diamond. Scientists estimate that up to 1/3 of the planet's mass could be pure diamond, that is, a diamond layer thousands of kilometers thick, covering a core of molten iron and surrounded by a thin crust of graphite and silicate minerals. If we could somehow bring a piece of this planet back to Earth, it would be the most valuable material ever found. But on 55 Cancri E, diamond is just ordinary rock. You might think this diamond planet is a peaceful, glittering world, but it is actually a violent place. Recent observations with the Spitzer Space Telescope show signs of intense volcanic activity across the surface. The extreme heat from the star and internal pressure create constant volcanic eruptions, spewing carbon-rich lava across the diamond crust. There is no water, no atmosphere that can support life as we know it, just a landscape of glowing diamond and molten rock. This planet teaches us that planetary formation is not limited to the patterns we see in our solar system. Where there is more carbon than oxygen, planets can become giant crystal spheres, challenging every assumption we had about rocky planets. Now, let us leave the glittering diamond world behind and travel to another equally bizarre exoplanet, the glass planet, HD 189733b. If the diamond planet is defined by its solid crystal structure, the glass planet is defined by its deadly, beautiful atmosphere. This planet is a gas giant, often called a hot Jupiter, located about 63 light-years from Earth in the constellation Vulpecula. It was discovered in 2005 and quickly became one of the most studied exoplanets because of its vivid blue color and terrifying weather. At first glance, HD 189733b looks like a peaceful, deep blue world, similar to Earth. But do not be fooled, this blue color does not come from oceans. It comes from clouds made of glass. The secret of HD 189733b's blue hue lies in its upper atmosphere. The planet's atmosphere is thick and scorching, with temperatures around 1200 degrees Celsius on the day side. Silicate minerals, the same materials that make glass on Earth, are vaporized by the extreme heat, forming tiny glass droplets high in the atmosphere. These glass particles scatter blue light much more effectively than red light, giving the planet its rich, cobalt blue color. But the beauty of this blue world hides one of the most violent weather systems in the known universe. This planet rains glass, not gentle drops falling from the sky, but sharp molten glass shards blasted sideways at supersonic speeds. How is this possible? Like 55 Cancri EHD 189733b is tidally locked, creating a massive temperature difference between the day side and the night side. The day side is baked by its star, while the night side is much cooler. This extreme temperature difference drives global winds that reach up to 5,400 miles per hour, or 8,700 kilometers per hour, about 7 times faster than the speed of sound on Earth. These supersonic winds carry the vaporized silicates from the hot day side toward the cooler night side. As the silicate vapor cools, it condenses into tiny pieces of molten glass. Instead of falling down, these glass shards are caught by the hurricane force winds and sent hurtling horizontally through the atmosphere. It is a never-ending storm of flying glass, capable of shredding any material that enters its atmosphere. NASA scientists have even nicknamed HD 189733b the Slasher Planet because of this deadly glass rain. HD 189733b is also a scientific milestone. It was the first exoplanet to have its surface temperature mapped, the first to be studied in X-ray wavelengths, and one of the first exoplanets where astronomers directly detected atmospheric components like sodium and carbon dioxide. This planet shows us that atmospheres can take forms we never considered. On Earth, rain is water. On Mars, it is sometimes carbon dioxide, snow. On HD 189733b, it is glass. This diversity of weather and composition is one of the most exciting discoveries in exoplanet science. When we compare diamond planets and glass planets, we see a beautiful pattern. The universe is full of endless possibilities. Both planets are shaped by extreme conditions, but they turn into completely different worlds. The diamond planet is a solid crystalline super-Earth built from carbon. The glass planet is a turbulent gas giant with a deadly glowing atmosphere. Both are close to their host stars, tidally locked and hostile to life as we know it. Yet both are incredibly valuable to science because they expand our understanding of how planets form and evolve. For decades, astronomers thought all planetary systems would be similar to our own. We expected rocky planets close to stars and gas giants far away. But exoplanets like 55 Cancri E and HD 189733b have completely changed that view. We now know that planets can be made of diamond, rain glass, orbit their stars in hours, or have atmospheres that glow with alien chemistry. Every new strange exoplanet we find is a clue that helps us solve the biggest puzzle in astronomy. How did our solar system form, and are we alone in the universe? The study of these weird worlds also pushes the limits of our technology. To detect and study exoplanets dozens of light years away, we use space telescopes like Hubble, Spitzer, and the James Webb Space Telescope. We use spectroscopy to analyze the light that filters through a planet's atmosphere, revealing its composition. We use computer models to simulate the extreme pressures and temperatures that create diamond layers and glass clouds. Every observation of a diamond planet or glass planet improves our instruments and our models, bringing us closer to answering the biggest questions about our cosmos. As we look to the future, astronomers will continue to find more bizarre exoplanets. There may be diamond planets larger than 55 Cancri E, glass planets with even faster winds, and other worlds we cannot yet imagine. Each discovery reminds us of the vastness and creativity of the universe. We are just beginning to explore the galactic neighborhood, and already we have found planets that seem like magic. Diamond planets and glass planets are more than just curiosities. They are proof that the universe is far more amazing, diverse, and wonderful than we can ever dream. They remind us that Earth is special, but it is not the only story. Beyond our solar system, there are thousands of other worlds, each with its own geology, weather, and history. Some are made of diamond, some rain glass, and some may hold secrets we have not even begun to understand. The next time you look up at the stars, remember, somewhere in that vast darkness, there is a planet made of diamond, glittering in the light of its star, and another blue world, where glass screams through the atmosphere. These are the strange, beautiful realities of our universe. And we are lucky to live in a time when we can discover them, study them, and marvel at them. Please like, comment, share, and subscribe to the channel.